Hello friends, in this video we will explain about order of the group and order of the element in the group. So we will work out lot of exercises from Damit and Foot. I have a list of exercises from 16, 17, 20, 21, 23. All of these are like very important exercise. We will work out everything. Okay, it is easy only. Okay, let's go through the definition. Before that, please subscribe the channel and please share to your friends whom you think this will be useful for you. Okay, let's do it. Okay, let's start. Order of a group. So order of the group denoted like this or sometime like this. I prefer this because this is exactly the cardinality. Okay, let G be a group. The order of G is cardinality number of G, that's denoted the set cardinality. Okay, it may be finite, it may be infinite. For finite cases only this is most interesting. For example, Zn, that is nothing but Z quotient by nz. From number theory or some other point of view you can understand the cardinality of this is n, and real cardinality is uncountable. People put 2 power l of 2 power l of naught. N cardinality people put l of naught. This is countably infinite. Z cardinality is also l of naught because this is set theoretically bijective. Okay, so this is the group order of a group. The order of the element is, okay, let x belongs to G be a element in G. Then order of x, I prefer Ox. Sometimes Damit and Foot uses this one, but I prefer Ox is defined. So this is very important definition. You have to be very careful about this. Define smallest natural number such that x power n, smallest natural number n such that x power n equal to identity. That means you collect all a belongs to natural number such that a power n equal to identity. I didn't finish the definition. Okay, first you do that. Collect this is, it may be empty case, empty, this may be non-empty. If it is empty, define O A sorry let me n x over n equal to this and choose the smallest one. Define a to be infinite, OA to be infinite if it is empty. If it is empty, if it is non-empty, that case 2, this is case 1, case 2 non-empty. Then you define like minimum or smallest n belongs to natural number such that x power n equal to identity. Okay, the smallest of them. Okay, so this is very important definition. The smallest is very important because, for example, let us take this group plus or minus 1 plus or minus I. People know this is a cyclic group of order 4. So I square equal to minus 1, I cube equal to minus I power 4 equal to 1. So the order is I power 4, and you can see that I power 8 is also can be written as I power 4 into I power 4, that is 1 into 1, that is 1. So I power anything multiple of 4 is like that. So that's why the smallest is very important, sort of defining the uniqueness. So if it is not, it is infinite. Okay, if such a n not exists and it's called infinite. Okay, let's do exercises. Okay, let's do the exercise number 16. I am using Damit and Foot book, Damit and Foot algebra. Exercise number 16 that says that let G be the group order of x equal to 2 x power 2 equal to 1. That implies order of x equal to 1 or 2. you can see that if order of x is 1, that means x equal to identity itself, nothing more than that. That means x square equal to identity into identity, that is identity. So it's fine, it satisfies. I wanted to prove if x is not identity and x power 2 equal to 1, claim order of x equal to 2. Yes, certainly order of x is less than or equal to 2, because x power 2 equal to 1, and order is the minimum element which satisfies this thing, because you see the number, the minimum, the smallest number, such the power. So the order of x is less than or equal to 2. Clearly the order of x cannot be 1. Why I am saying, because x power 1 equal to identity means x equal to identity, but I have taken not identity, so that implies order of x must be 2. So this is one of the exercises in dummy food, very easy. And 17th exercise is like let x belongs to the group with order of x. Group may be infinite, but there are finite order elements may be exist. There are many groups you can in fact think of. So later on we will see the examples, but we will see the definitions. Now we will get the very concrete understanding of the definition by exercise. So order of x equal to 1 n, that means x power n equal to 1, and this is identity, this is the smallest thing that satisfies. Okay, climb x power, this is x power n minus 1. It is easy because x star x inverse equal to x inverse star x equal to identity, and this is unique. So in our case, x power 1 star x power n minus 1 equal to x power n minus 1 star x. So it's the same element, so it can commute. So this is x power n minus 1 plus 1, this is x power n, that is equal to identity. So instead of here this element satisfies this condition, so that implies uniqueness of inverse says that x n minus 1 must be x power minus 1. Okay, so the definition that we proved last video about properties, the uniqueness of inverse helps us here to understand this. Okay, so let's go for 17. Exercise 17 says that order of x n, group is infinite or finite, doesn't matter, group is there, and okay, sorry, I have proved 17th only here. Okay, now I have to go to 18th. Not 18th, some other example. Okay, let's go for 20. 20 is like let x belongs to G. Suppose I want to say that order of x is same as order of x power n, x inverse. Okay, climb order of x same as order of x inverse. Proof. Suppose infinite, case 1, x order of x is infinite, that means there exists no, that means x power n not equal to identity for every n belongs to natural number. Okay, so it's clear that if x inverse minus k equal to identity for some k belongs to natural number, that means x power minus k equal to identity, that means x power k equal to identity. You roll this one by one, x like this, like x power minus k can be written as x power minus 1, x power minus 1 x power minus 1 k times, then that is identity. Roll this one, that will become x k times k minus 1 times, that will become s. So pull slow one by one, then this side becomes x power k, but we say that there is no n such n, so there is such k cannot be exist. So that clear implies that x inverse order also not finite, which I mean x power k not equal to identity for every k belongs to natural number, that says that this is infinite. So case 2, x power n equal to 1, the order of x equal to n. So this is the case 2. Claim the order of x inverse also n. Okay, so let's take L equal to order of x inverse. It is clear that x dot 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 x n times equal to identity. This is the definition and smallest n. So then slowly you pull back x inverse, x inverse, x inverse. So that means here we will get identity x inverse, x inverse, x inverse. This is n times. That means order of x inverse less than or equal to n. See, we have proved that if I multiply n times, then we will get identity, but we wanted to get smallest one. So from here we can understand that this is less than or equal to n. Suppose, let's say this is L. That means x minus L equal to x minus 1 dot 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 x minus L times. So this is equal to identity. So slowly pull back x. So x power L equal to identity. That says that order of x, that is n, the smallest one related to x, is less than or equal to L. So from here we can see that the equation number 1 and equation number 2, L equal to n. So this is what we wanted to prove. Okay, and the 21 says a very nice thing. The example 21, exercise 21. Exercise 21 says that let G be a finite group. Okay, and x be a order, x be an element of G of order n, and n is odd. Then prove that x equal to x square power k for some k greater than or equal to 1. Okay, proof. So remember that I don't know how G finite group is going to be useful here, but because if G is not finite also, the group generated by x is finite and we can work with this. So that is what I wanted to do. The main thing I wanted to understand that n is odd. That means 2L plus 1, where L greater than or equal to 0. This much we know. Okay, and I know x power n equal to identity. So what I am doing, I am rewriting this thing 2L plus 2 minus 1. That is, I am just adding 1 and separating 1. 2L plus 1 minus 1. So I know x power n, that is equal to identity. That is 2L plus 1 minus 1. That is x 2L plus 1 x minus. So now take this is here. So x equal to x 2L plus 1, and now our k equal to L plus 1. That's what x 2L plus 1, that is x 2k. It's clear, right? x 2k. So this is what I wanted to prove, and clearly k is greater than or equal to 1 because L starting from 0, so L plus 1 is going to be greater than or equal to 1. So I'm done, it's proved. Okay, final exercise is like 23, and not is final, I wanted to do another one. 23 says that let G be a group and x belongs to G. Order of x equal to n. The order of x equal to n, and n can be written as st. St belongs to natural number. Then x power s, the order of x power s is t. Proof. This is a claim. Proof. So I wanted to show that, okay, let's take L equal to order of x power s. I want to show that L less than or equal to t and t is less than or equal to L. That's clear. Let's see. X power s t times. It is nothing but x power st, that is nothing but x power n. You see this? So this is nothing but identity. So certainly L is the smallest one because L is the order. The order of x power s is less than or equal to t. Now let's do this once more in the reverse way. I want to show that t is less than less than or equal to L. T is less than or equal to L. So suppose not, T is strictly less than, sorry, L is strictly less than T. That means SL strictly less than ST, right? This much is clear because S I'm multiplying, S is greater than or equal to 1. And I'm see, remember that I have taken from natural number, not from whole number. So it's like minimum greater than or equal to 1, strictly less than this. So x power s x power s dot 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 x power s L times, by the definition of order of x power s, this is identity. That means x power ls equal to identity. That means order of x ls, I mean the order of the x, what I'm saying, that order of x is less than or equal to ls, which is less than st, which is equal to n, which is a contradiction because n is chosen to be the order of x and that must be the minimal. Now we produce another minimal guy, which is not possible. So this L times, which is not able to achieve, so L must be greater than or equal to minimum t. Otherwise, if it is less than t, it will be a huge problem to the n. So L must be t. So we are done. Okay. Final thing is very well known that prove that x power 2 equal to 1 for every x belongs to G, then G is abelian. Proof, this is very simple. Let's take, I want to prove that A dot B equal to B dot A. I'm doing this exercise because here it's related to the order, irrespective of G is finite or infinite. Okay, this is a claim. What I know, A dot B the square whole square equal to A dot AB, but that is equal to identity, right? That is equal to identity. Okay, so AB equal to A square B square. This is B, because this is also identity, this is also identity, this is also identity, doesn't matter because it's a AB square. So we have AB equal to BB. Now use the cancellation law. Let's cancel one by one the both end. We will get BA equal to AB. So this is what I want to prove, right? AB equal to BA, both are same. It's a symmetricness of the equality. So AB equal to BA. So that done. This implies G is abelian. So this kind of things will help you in many cases in the later on system. Okay, these are the things I wanted to do today about the order. So we got some idea about order and how to work with the order. And remember the definition. This is one. The very important thing is the minimality. Minimal. If exist such a number exists, is called the minimality. Very very important, that minimality. Okay. In fact, you can prove that. You try this. You can prove that if order of x equal to n, then suppose x power L equal to identity, then n should divide this L. That means L is nothing but some multiple of n. Okay, remember this is smallest. Okay, you try this exercise. You have to use this Euclidean that idea. Every number you can divide plus a remainder either 0 or less than the divisible this guy. Okay, I remember that this n belongs to natural number. This cannot be 0. Okay, thank you. I hope that you like this video. Please share this video, subscribe the channel. You share as much as you can so that it should go to the people. It's in the level of BSc. Slowly we will make a difficulty level so that you can seriously work out with these problems in the CSIR and NBHM related competition exams. Okay.